Assalamu alaikum. Welcome to my video presentation on simple as possible architecture design, which is SAP 1. And in this design, our task was to design a 6-bit SAP. And this is the design. This is the whole structure of the 6-bit SAP design. So I will be explaining bit by bit of the components and the procedures we use in carrying out this design. First of all, we have some specifications in this design. One, we use a single 6-bit bus bar for both the address and the data transfer. We use 8 by 6-bit RAM, which is random access memory for storing the program and data. We also use a program counter for containing the address and also to execute the next instruction given. And the counter will be counting, since we are using 6-bit and RAM is 8 by 6, meaning it will be counting from 000 to 111. We have both our input unit for writing the program into the RAM before running the computer. We also have MA, which is the memory address register for accessing the RAM data. We also have ALU, which is the arithmetic and logic unit, which is capable of both addition and subtraction of the 6-bit. And we are using registrars, and the two registrars we are using, registrar A and registrar B. Registrar A is the accumulator, and we have registrar B. Both of these registrars are 6-bit registrars, and these registrars are used for storing the data for the ALU operation, meaning they will be storing the data for the arithmetic and logic units to carry out its operation of both addition and subtraction. Also, we have a control unit for controlling other blocks of this design. We also have an output unit. This output unit is capable of showing the output in binary form, because we have input and the output. Whenever we inputted any value, we want to observe what will be the output of that value. And after explaining some of these basic specifications in this design, I also want you to know that we have the clock signal. We have the clock signal, and in this clock signal, we have two main different types of clocks embedded in this design. One, this is the clock signal, okay, the main clock signal. And in this clock signal, we have both the manual operation and the automatic operation. So this is the clock pulse or the clock signal. Okay. So now, as I explained earlier on, we are using this clock signal to generate the clock pulse. And in this case, we are generating both the clock pulse in manual way and the automatic way. If you want the clock pulse to be manually. As I was explaining, now I want to take you through the program counter. I have explained about the clock port. Now I want to explain about this, the program counter. We already know, since we are preparing a 6-bit SAP 1, meaning we need a program counter of 3 bits. We already know that from the word program counter, meaning this counter will be responsible to count numbers from 000 up to 111. That is the job of the program counter. And after counting, it also stores and sends out to the memory address so that the next instruction will be fetched and executed. This program counter will also increment values after each instruction cycle. This program counter here. Therefore, as I made mention earlier of the program counter and its function. So you have inputs, since we are using 3 bits, since this one is a 3-bit program counter. So when you input your values here, these values will be stored, and these stored values will be sent to the memory address for the values to be executed. And after this program counter, let me show you, we have the MA and the inputs. So this is the MA, this is the MA, and this our 2 inputs. We have the clock here. As we already programmed the clock, all the other clocks in these blocks are connected to the main clock block. So here we have 2 inputs here, and we have the MA. The MA, these 3 outputs of the MA are connected to the address selector. And also this input of the inputs, we have 3 inputs here. These 3 inputs are also connected to the address selector. And the address selector is connected to the RAM. The 3 outputs of the address selector are connected to the RAM. While the inputs, 6 inputs are coming from the input directly to the RAM. So as you can see, initially we have 3 inputs that are connected to the address selector. We have 3 inputs that are connected from the MA to the address selector. From the address selector, we also have 6 inputs from the input to the RAM. And we have 3 outputs from the address selector to the RAM. We have RAM 1, RAM 2. We are using 2 RAM in this design. Over here, as you are seeing my cursor, these are the inputs, 6 inputs coming to the RAM. 3 to the RAM 1, 3 to the RAM 2. We already know for the RAM, it has read and write mode. Read and write mode. So, this is the basic idea in relation to both the program counter, the MA, the input, address selector, and the RAM. So now, let me take you through the accumulator. We have the accumulator and the ALU. As you can see, we have 6-bit bus bars. These are the bus bars. We have 6 of these bus bars. And for the accumulator, 6 bits are coming to the accumulator as input, and also 6 bits is coming from the accumulator to the bus bar. So this is the accumulator. As you can see, these 6 are the inputs that are coming from the bus bar to the accumulator, and the output 6 of the output from the accumulator to the bus bar again. And 6 bits again is coming from the accumulator to the ALU for it to perform its operation of either addition or subtraction based on the instruction given to the ALU. 6 bits is coming from the accumulator to the ALU, and 6 bits is coming from the ALU going to the bus bars. As I'm zooming, 6 bits coming from the ALU to the bus bars, and from the bus bars, from this bus bar, 6 bits is also coming from the bus bar to the B register. This is the B register. 6 bits from the bus bar coming as input to the B register, and also 6 bits is coming from the bus bar to the output register. This is the output register. And the output register is connected with the binary display. This is the binary display. So as I was explaining, 6 bits is coming from the bus bar to the accumulator, and 6 bits from the accumulator back to the bus bar, and from the accumulator again, the accumulator is sending 6 bits to the ALU for it to perform its operation, and the ALU is sending its output to the bus bar, 6 bits, and 6 bits is coming from the bus bar to the B register, and 6 inputs again from the bus bar to the output register, and the output register has been connected here with the binary display. So in this design, the 2 other blocks that are yet to be explained are the instruction register. As I made mention earlier, the functions of the instruction register. From the word instruction, it is instructing the whole design. It is giving instruction to the design. Okay, so this is the instruction register. The instruction register, as we can see, let me zoom very well, 6 bits is directly coming from the bus bar to the instruction register, and also 3 bits is coming from the instruction register to the bus bar. 6 bits from the bus bar to the registrar, and the output will be 3. It is giving 3 outputs back to the bus bar, and the other remaining 3 will be coming to the controller sequential. This is our controller sequential. 3 bits are coming from the instruction register to the controller sequential. This is the controller sequential. This one controls the overall activities of the whole SAP 1 6-bit design. So therefore, this will be the end of my presentation. I hope you learned something from the whole presentation. Therefore, this is the end of my presentation on this SAP 1 6-bit design, and I want to give a special thanks to our course teacher, who is Professor Nadim Ahmad, and to our project supervisor, Mr. AKM Rakib. We are really thankful and grateful for your efforts and guidance to ensure this whole project becomes a success. Once again, I am your presenter for our team, Team 5, which is comprised of 6 members. On behalf of them, I want to say thank you and thank you very much. I am Alusainba. Thank you once again.